Here's our displacement time graph from class, from Dylan and Eitan, who were trying to walk towards the sensor with a constant velocity. You can see that Eitan is not a greased swan on rails. He doesn't glide. He takes actual steps, and as hard as he tries, this is just about as constant as a human being gets. We're using this graph to check the sensors. If they don't follow the laws of physics, they're not worth much, and we shouldn't be using them in the lab. We took notes on our basic graphing conclusions from graphs and from calculus that the slope of a displacement time graph in meters per second, change in y over change in x, translates directly into instantaneous velocity. Meters rise over seconds run. Therefore, if Eitan is trying to walk at a constant speed, then his average velocity should be the slope of the line segment. This is pretty cool because the calculator gave us a best fit line for Eitan's graph. And it looks like this. The calculator gave us a best fit equation for Dylan and Eitan's graph. It said that the displacement on the y-axis was equal to negative 0.59 t on the x-axis plus 2.68. Now, if we use our formula for average velocity, the one we got from the notes, the one defining the average as final change in displacement over total change in time, we ought to be able to predict the physics. Use the data from the board. Note that change is final minus initial. In this case, final's displacement minus initial displacement over the total change in time. Total change in time is easy. We can do it in our heads. The total change in time is clearly 4.34 seconds because that's when they started the stopwatch. They started the stopwatch at 0. And interestingly enough, their group didn't take the full 5 seconds of data. Now plug in the final displacement, the one at the end of the line, when Eitan was almost back at the sensor, and the initial displacement of where he started all the way at the beginning, and you should get your average velocity. Type it into your calculator, press enter, see what you get. Check your numbers. Are they what they should be? First and foremost, does the number you get for your velocity reflect the fact that Eitan was walking backwards? He was walking towards the sensor instead of away from it. Check your chart. You were expecting a positive number or a negative number for your average velocity. Did you get what you expected? Now, somebody asked in class about 2.68. 2.68 is the y-intercept. The y-intercept should be where he started. But here we can see on the screen that he started at 2.75 meters, not 2.68. The calculator says, well, I did all the averages. I could have sworn he started at 2.68. That would make the average work out. Well, we're telling the calculator your average is a little bit low. This is our first indication that either the data is not perfect or Eitan is not perfect. He is human. He takes steps. Notice that sometimes this line dips below the average. The calculator's like, no, I don't live in a world of real people. I live in a world of data, and it adjusts the data to fit Eitan's average. This is our signal that we are definitely going to need a percent error. Not only are we checking to see whether the value is what we expected, we're checking to see if it's consistent with the measurements. Was your average velocity almost the same as the slope on your graph? Almost. In class we said to 1 sig fig because we are measuring by meters. We don't have a laser guided timer here to measure Eitan's steps micrometer by micrometer. If they were almost the same but not identical, then find your percent error. You watched the video on RZJHS Physics about percent error, and it said there were 2 formulas for percent error. One of them is when you have an official textbook value that's been verified by the Système International in Paris, that's found all over the materials, all over the web. Everybody knows this is true. This is practically infallible data. This is the mass of the electron. This is the universal gravitational constant. It's called universal for a reason. People much older and more experienced than you have measured it. In that case, you hold that measurement as an international standard and see how far you deviated from that standard. However, most of the time, if it's been measured by millions of people all over the world, why do you have to measure it for a first-year physics class? Just look it up in a textbook and go. Most of the time, you're making new measurements yourself about your speed, about the traction on your shoes, about the index of refraction of your particular piece of plastic or glass, things that have never been made before. Typically, there are two values, one that you measured in the lab with your equipment, and one, a calculated value that you worked out based on official numbers on the calculator. Why is the calculator's value suspect? Why isn't it a perfect international standard? Because I'll bet you anything the numbers that you plugged into your calculator came from your lab or from somebody's lab. I ask most of the time whether students are more confident in their calculations or their measurements. It generally comes out 50-50. You've got people who are clumsy with the equipment saying, no, I'm going to go with the calculations. And you've got people who are math phobic saying, no, I might have lost a square root somewhere. Why don't we just go with the measurements? They're both prone to error. What you have is two values. You can't measure either one of them as an international standard, so you find the average between them, and you find it first, and you put it in your denominator. You should find the average between the official slope of negative 0.59 and the average velocity you found here. When you find that average, it will go in your denominator. Negative or positive, it doesn't matter. That's what the absolute value means. Absolute value means it doesn't matter whether it's negative or positive. Just put in the number and find the difference between them. You'll have a first value, usually the one you measured yourself. You'll have the second value, usually the one that comes from the calculator. And it'll give you a decimal. The difference between 0.60 and 0.59 is ridiculously small, but find out how ridiculously small it is. Multiply your decimal times 100 to get a percent error. If your percent error is very, very small, if it is, as the video said, less than 5%, then your data is exceptionally good. If your data is exceptionally good, then the sensors are working, and we can derive the rest of what we know about the laws of motion based on these sensors and not be worried when we start speeding up and turning around and backing around U-turns to make sure that everything is all right. The one thing we do have to check before we go much further forward is the way that we're using words and numbers. The questions in your big lab conclusion give you the formula V equals D over T. Some of you took notes about that in class in large capital letters as to when you should and shouldn't use this formula. Compare this formula, real formula for average velocity. Proofread that formula like the devil. Is the one printed in your lab packet correct? If not, what's wrong with it? And does the average hold for every single point, even if it is correct? Is that the slope of every point of the straight line on your graph? If not, what good is an average? Is it true for any point? When you've proofread the formula, make sure that your average is measuring the change in displacement from start to finish over the total change in time. And you know when to use that average when the going is good. And when your data clearly deviates from the average, you are in good shape and ready to analyze the rest of your data.